talk about set theory today. And set theory sounds very complex in a lot of ways, but it actually is basically a theory of making lists, seeing where list and categories overlap. So we're going to be able to define them, write them in different ways, define the empty set. We're going to say what is cardinality and how do we find it, and we'll be able to classify sets as finite or infinite, and then talk about equality of sets. So a set is really just a collection of objects. And by objects, we mean items. So like a list of states, a list of addresses, a list of the different types of soda. In our study of sets, we're going to restrict our attention to sets that are easily defined with clear characteristics. So that means that there's an easy answer. Does this belong here? Yes or no. So if I'm making a list of soda and I want to add pot roast to it, pot roast does not fit, so it is not a part of the set. There are some sets that are a little more ambiguous, but we're going to stick to being clear and crisp. Every item in the list is called an element or a member of the set. So if I have a list of soda and I have Dr. Pepper in there, then Dr. Pepper is an element and it's a member of the set. So the roster method is where we take the elements of the set and we list them between what we call braces. So not brackets, but above the bracket on your keyboard, that's a brace. And we put commas between each element. So instead of listing things vertically in columns, we just literally make a list. So if you were making a list of items in your essay, you would use commas to separate them. An order for a set doesn't matter. So let's try this out. Let's write the set for the months of the year that begin with the letter M. Is it well defined? Why or why not? Well, there's only 2 months that begin with an M, March and May. And notice these are called braces. In Alex, you're going to want to make sure you have a space between your comma and your final word. Is it clear? Well, we clearly know if something starts with an M, so yes, it's a well-defined set. And for our purposes, we're going to stick to those easy answers. So how does this relate to actual math and numbers? Well, sets can be classified with the types of number sets that we have. So we typically use a capital letter when we define a set. And so if I was doing natural numbers, it starts with N, so that's why I chose the letter N. Natural numbers are all the numbers that we count, so 1, 2, 3, 4. When we have numbers that continue on or things that continue on a list, we use the ellipsis, which is 3 periods. So any set of numbers, for the most part, is going to have an ellipsis, unless you are looking at a set of numbers like all the multiples of 5 less than 25. That's 5, 10, and 15. So there's a finite list of those numbers because I put a cap on it. So let's look at this. How would I write the set of natural numbers less than 6? Well, first of all, there's a cap, so we're not going to have an ellipsis. So that would be 1, 2, 3, 4, and 5. Let me get back to that example. And then if I was looking to write the set of odd natural numbers greater than 4, I'm going to start at 5, 7, 9, 11, and there's no cap, so I have an ellipses. Can you think of another way to describe each set in words? So I could drop off the word natural number and use things like counting numbers. So, or I could say numbers between 0 and 6 or greater than 3. So just a little bit of a play on words. In set notation, you really kind of have to translate it like it's a different language. So the symbol, the E, is used to show that an object is a member of the set. So if A is the name of a set of the days of the week, then we could write Monday is an element of A. So the E, think of it as element. So Monday is in the set A. Or we could also say, likewise, Friday is in the set A. So if I want to take this and put it into set notation, I could decide whether this is true or false. Oregon is contained in set A, where A is the set of states west of the Mississippi River. So pull out your geographic maps right now, but it's true. It is going to be a set west of there. In part B, 27 belongs to the set. And if I look at that pattern, 1, 5, 9, I'm basically doing every other odd number. So if I continue from 17 and I do every other odd number, I'm going to get that it's not in the set, because I'll have 21, 25, and 29. And then Z is not in the set, V, W, X, Y, Z, and it obviously is in the set, so that's going to be a false statement. So additional ways that we can use a set, we have the roster method where we're listing items. We have the descriptor method where we're describing them in words, and then set builder notation is what we just showed. So if I want to look at describing a set with the descriptive method, and I have the set containing 2, 4, 6, 8, 10, and 12, so I could say all of the numbers in the set, well, they're counting numbers, and they're all less than 14. So B is the set of numbers less than 14, and they're even, so we include even in there. We could also describe them as the set of numbers between 1 and 15 that are divisible by 2. That's another way to look at it. The third and the fanciest way to do it is set builder notation. So a variable is a symbol with a letter that represents the different elements of a set. So we like to use the letter X. So the way that I would actually read this right here is X such that X is an element of the set in and X is less than 7. So that is how you would actually read this piece out. We typically use X. It's just the most common variable. There's no specific reasoning here for why. So let's look at using the set builder notation for the two examples. So in the two examples, I want to have my parameters filled in that it has the numbers 2, 4, and 6. So I could say X such that all X values are even natural numbers and they're less than 7. So the notation also has to go with the explanation here. It can't live alone. And then I have the set W contains the elements red, yellow, and blue. And so if I think about that, I could say, well, then it's primary colors. So the set of all X such that X is a primary color, those three things are included in that set. So now let's look at how to use the roster method to describe that set given. So if I describe the set given in roster, I'm just going to put the braces and actually list the values. If I describe it in words, I could say the set S is the set of all the natural numbers greater than 31. And if I wrote it in set builder notation, I'm going to use X such that X is an element of set in and X is greater than 31. So if I want to write a set using an ellipsis, so now I don't want to look at an ellipsis at the end. Maybe my set is too many numbers to list and I don't want to write them all out. So an ellipsis can actually be used between the values of a set. We also have what we call the empty set, which may seem to be very intuitive. But there are some sets that have no answer. There's no value to them. And so we call it an empty set or the null set. And so we use the braces with nothing between them, and that shows that it's empty. Or we use the null symbol, which is the circle with the line through it. So which of the following sets are empty, meaning that nothing meets the criteria of the set? So I have the set of woolly mammoth fossils in museums. I'd probably have to Google that one. There's a fossil somewhere, so the set is not empty. Woolly mammoths have been extinct, so if I look back at letter B, there's no living woolly mammoth, so it's going to be the empty set. And then if I look at C, that one's tricky because the null is the set that contains the empty set. So it's a little goofy, but essentially it's true. And then this set is empty because there's no natural number between 1 and 2, because there's no number I can count that's not a decimal between 1 and 2. So the cardinal number of a set sounds more complex than it actually is. We show the cardinality, so the operation is n of a. So the set variable would be a, and n is going to make sense in a minute, and it's just the number of items in the list. So n stands for number. So if the cardinal of a set is just counting how many things there are, so in the example we gave you, there's 5 things in the list. Now, if I want to do it with these items, A is actually quite easy because I can just count it up. In B, they gave me set builder notation, so I'm going to have to actually handwrite that set out. In C, again, I've got an easy, clear list there, and then D is the empty set. So there's 6 items in A. If I actually list out the items in B, I get there's 15. In C, I have 1 element. And then in D, there are no values in the empty set because it's empty. So a set is finite if it has no elements or has a cardinality that is a natural number. So meaning that there is a clear number of items in the set and it's not infinite. So a set that is not finite is then by default infinite. So if I'm listing all the multiples of 10, that list would just keep going on and on and on and on, and there wouldn't ever be an end to it. So that would be an infinite set. If I want to classify sets as finite or infinite, I have to basically look at, is there a cap? So if I look in A, there's a cap because x has to be less than 100. So that's going to be finite. In B, the set of letters used to make Roman numerals, you may have to actually look that up, but there are a limited number of numerals. So that is finite. If I look at C, that ellipsis there tells me it's infinite right off the bat. I only have a limited number of immediate family members, and a lot of different songs can be written, so that's going to be unlimited. Equal and equivalent sets means they have the exact same elements in them, not the same number of elements, the exact same items in the list. So if I look at A, they don't match up. If I look at B, they match up and order doesn't matter, so they're equivalent. C, they don't match up. 213 is not the same as 2, 1, and 3. And set D, it looks like they are close, but no dice because there's not an 11 in D. And if I look at even natural numbers less than 10, that is the same as the list given. All right, so one-to-one correspondence of elements in a set means the first set can be paired with one element to the second set. So it's almost like mapping them onto each other. So do the sets 8, 16, 24, and 32 have one-to-one correspondence? So if I wrote them vertically on top of one another, I would be able to see that there's one item that corresponds to each one. So one possible way to show that is the diagram below. If I look at the second example, there's different numbers of elements. I can't map them to one another because I have 3 in one and 2 in another. Even though they're not equal and they're not related, the issue is more that they have a different number of values in their set. And so what does that mean? What can I actually conclude is that they have to have the same number of elements. And so when I talk about one-to-one correspondence, I'm basically saying, do they have the same number? So 2 sets are equivalent if you can put their elements in one-to-one correspondence, and they're not equivalent if you cannot do it. So that's going to be a simple way to look at it.